Hello everyone, welcome to my channel Security Beast. Today we are going to solve the next challenge of the series that is called a Stack5. So this challenge is really difficult and not super difficult, but this is still difficult, and you have to keep in mind a few things that this is the first challenge which is going to mess with ASLR settings. So we have to disable the ASLR for this challenge. Second thing, don't get nervous if your shellcode is not working or you are getting the illegal instruction error, because this is supposed to be happen as we are not supplying any arguments to shellcode. And if you want a video on how to create your own shellcode, just let me know. Okay, so let's not waste our time and start our video. So it took a while to understand this challenge, so and took a lot of effort to solve this. So let's jump into challenge directly. First thing what you should do once you start this challenge is disable the ASLR. So how you will disable the ASLR? Using proc sys kernel and randomize v. Just check the first what is the current state of ASLR. This thing really mess with your shellcode and address. Okay, so make sure that you disable the ASLR for this challenge. Okay, so I'm disabling the ASLR by just appending 0 on the proxys kernel randomized VA space. I have created a video on ASLR too. So if you want to learn how it works, the video is already there. Okay. Now, once you disable the ASLR, I suggest you to compile your source code with some additional option. Okay, like two more option, two important option for this is like first one is no stack protector, and second one is no PIE, position independent executable. Okay, so I'll show you here. So you can compile the source code with this option of GCC, GCC stack5.c output is stack5, and here we will say executable stack and no stack protector and no position independent execution. Okay, so why we need this option? So as a security best practice, this option should be enabled. Okay, but here we are saying that yeah, we need a vulnerable binary, that's why we are compiling it here. So when you compile this binary, you will get this error messages. So like the gets function is dangerous and should not be used, because these are known as the native vulnerable functions in C. So that's why. So let's take a look at the source code as uh, is it deleted the source code? No. Okay. Stack5.c. So let's understand the challenge here. It is just saying there is a no winning statement here. So like we don't have to call any function or we don't have to give the address after buffer. So this is a real time hacking. This is a real hacking where they have given you the buffer of 64 byte, which you need to fill with your pattern. Okay, or then plus 4 byte, and so regarding challenge, this is calling the gets function, which should not be used. Gets buffer. So what it reads the standard input output, that is stdin, that is input what we supply to the program, and it send it to the memory. And since there is no validation, such as no size of function is used, or no malloc is used, or free is used, like no proper, there is no sanitization at all. It's just like you take the input and call the gets, like call the input in memory. So this is the classic vanilla buffer overflow. But when we are doing it with ARM, we have to consider a few things. Like it's not as plain and as easy as we do it on x86 or 64. Second thing, we have very limited resources for this. So you have to like if you lost in while exploiting these videos, if you lost while exploiting any challenge, you are lost unless you put a lot of effort to understand this. So that is also a primary purpose of me making video on this. Okay, so okay, so once you compile this binary, if you see, it takes a lot of input. I mean, it takes an input, send it to buffer, and it gives seg fault. Now let's take a look at it in GDB. Okay, how it looks. So our GDB is enhanced GDB. So now by solving the previous four challenge, we know the buffer is sometimes 64 and 68. So what I want to do is like disassemble main function, and here we see the gets is getting called. So I want to put the breakpoint after gets, and after gets I want to see what it does here, like how it is moving in memory, and before exit I want to put one more breakpoint. So what will be the final state of registers when we exit this. So let's create one sample payload like Python uh, -c command line, and call our friend print, and print k into 68 times plus, so 64 is for this buffer and 4 is to overflow it. So, okay, plus I want to see what it does, like uh, what spaces we get. So I want to call A for 8 times and B for again 8 times, just to see the address mapping, where it goes, and where we will get space to host our shell code. And let's save it as a T1 test 1. Oh, C is not defined. Okay, B should be 8 times plus C again 8 times, C into 8. Okay, now run this video, sorry, run this program, run this payload, and run this program with this payload. Okay, and see what we get. Okay, so we can see here the gets function has been called successfully, and it loaded the value of k in memory. Then also we can see few c's here, and b is yet to call. That means that means we have to wait till b. Okay, now let's see what happened in next call. Nothing interesting. Oh, here you see the C is called again here. Okay, it is same state. So let's finish this program, and here we can see the B is loaded, CCC is also loaded, and B is in this R11 register, and A is at the stack, A is at the return address. So that means our return address, like the value of return address is already written here. So it means if we add 64 plus 4, those 4 values will come to here. Okay, now let's check the breakpoint again. Yeah, now run this program again, just for our references, just for our reference that how it working. Okay, execute, continue, execute, and yeah. So the A buffer has been here. C, this is the place where we can host our shellcode, which will get called here. We can also do one thing. We can check this with the create pattern create command, which is built in. I just learned this. Learn this. So we can create the pattern, and we can save this pattern again with T1, same name. Okay, now run the program with T1 to see where what things goes to memory. Okay, so this we reach to the exit of program. Now we will try to match the values. So here I'll take this 4 byte R, and we'll try to match with the pattern offset. So 60, yeah, 65th, it starts from 65th. So 64 is buffer, and 65th is like this value where we can call something, and this YAB is at 196. Okay, Now next instruction, the return pointer is still not written. Yeah, here. Let's see pa, it's calling pa. Pa is at 57 and here it is showing 60. I think it's missing something. Okay, but let's see. So we will be storing our shell code into the stack pointer. Okay, let's see the address of stack pointer. It's at sa. So 69. So after 68, we can keep our shell code. Okay, and this is the return address which is at 57 and 60 here. It's showing strange. For safer side, I think after 64 the return address should be there because 64 byte buffer is there. Okay. So what we need is we need a buffer to overflow first. That is at 68 or 64 byte. We'll finally we'll identify this. Then the return address and shell code. That's all we need to solve this challenge. So we will put our shell code in the stack pointer and we will instruct return pointer like PC register to call the stack pointer in the end after buffer so that we can execute the shell code from stack pointer. Okay, so let's just do it again. To simplify this, I can create one more payload simply. So to explain this, so let's assume we are starting now. -c print, so a into 64 times. So this is our buffer, okay, which we are going to overflow, plus this should be our return address b 4 times or 8 times. Okay, let's take it 4 times. Okay, plus c, this will be our shell code which is going to store at stack pointer. Okay, so c into 4. Okay, and now write this as a t1 and now run the program again. T1. So this ABC is always easy to identify and a lot of people get familiar with X41 and 42 and 43. That's why I'm doing this. So till the last program reaches the last. Yeah, now we are at the last. So here you can see at the B location we are going to host our shell code, and here the PC sorry, at the C we should be able we will be hosting our shell code, and at the C, one second, yeah, so you see BCCC, this is wrong. Let me just see the payload. So we have to add 4 more bytes here because you see the B address should be the return address and it should start here. It should be the BBBB because we are overflowing the buffer and we are calling the return address. Okay, so A into 68, B into 4 return address, and C is our shell code. This is just for example. Okay, now let's run this again. Yeah, so yeah, this sounds perfect. Okay, so here we have B, that is return address. Okay, and this is the buffer which we just overflowed, and this at the stack pointer we are going to host our shell code. Okay, I don't know why this 40 is here. It should be 4242. Okay, okay, let's not that's not important. So like what we identified is like we need a buffer of 68 byte, I mean 68 characters, and then the return address and then the shell code. Okay, and if we do this it should be working. Okay, so I'll show you my shell code first. Okay, first we need a return address, right? So this is our return address BEFF F418. Okay, this address we need to call, and after that we are going to use our shell code, host our shell code, and this is the I mean we have to call this address here after the buffer. So let's write an exploit for this. So like Python -c and print, we want to use a 68 times plus return address. So we should write a return address in Little Indianness. So it should be inverse. So how we'll write it? Start from 0xBE, then it should be /x ff, then /x f4, then /x 18. So this is the return address which we need to write here, and after that we need our shell code, and it is here. I already kept my shell code here. Yeah, this is the shell code. If you need how to create a shell code video, just let me know. Okay, I'll create one. So this is my shell code. Okay, and now this should work. So now save this as an exploit or whatever you want. Okay, it is saying that print is not terminated properly. Okay, and the address is not defined. How many mistakes, man, in one video, small video, and lot of mistakes. Okay, so I just forgetted this. Okay, so now our exploit is ready. We have 68 byte of buffer, then our return address, then our shellcode, and this should be work. This should perfectly work. Okay. Now let's run this. Just check for the breakpoints. Yeah, we have 3 breakpoints after gets and after some transmission is done and before exit. Okay. Now let's run this. Starting program. As the gets call is done, that means the input what we have supplied to the program is already loaded inside the memory. So let's look at the stack, how it looks. And I want to examine the stack, I think 64 byte with the raw address, and see what it looks like. Yeah. So as you can see here, your favorite X41 is here. So these are the this is the buffer what we have given. So 4141, this is a 68 times. After that we have given the return address which is here. You can see this return address clearly, BEFF F418. And after this is the start of our shell code which is starting at 418, right? This address which we have given here. So now this is our shell code. You can how to read it, like let me just show you my shell code, or we can check my shell code. Yeah, you see, if you read this address starting E28F3001, it starts exactly here, E28F3001. And you can so when you are developing the exploit, you should verify it, line by line, so that sometimes what happens is like you just type one line extra or one space or one character get missing and you keep debugging the program 1,000 times, and then you understand, oh, it was a typing mistake. So to avoid this kind of frustration, you should always verify your shellcode 2 times, 3 times, 4 times, 5 times, or every time. I do it generally. So if you see here 2F, this is our last 2F 737368. Here is the 68 and 58. Okay. So now we'll go to the next instruction, and so the stack pointer is currently at BFF54. So even we are yet to reach our series. I'll just zoom out for more clear view on registers. So next, okay, nothing much. Now this is interesting. You see here the PC, we managed to call it to our return address. So our return address, whatever we have given as an input, it's called here, and you can see our exploit here. So you can see the whole shell code which I just showed you, but still we can see again. So you see it starts here 3001 8F E2 E2 8F 3001, and this is our bin slash sh. You can see here, it's here somewhere. Okay, so the next step I am expecting is shell. Oh, no shell. Oh, still processing. The PC is here. Now the pointer has moved to here, and now we are at shell, and now we should see the shell call. Oh, something happened. Oh, it's not able to identify BFFF24. What is this behavior? Okay. Oh, so it's expected to get this kind of surprises. It's not, we are not like a Kotlin that you can write the code right away. Okay, let me take this again. And now let me continue the flow. Yeah. And here you go. Voila! Finally, we managed to execute our shell. So you see here. So there is a trick. I don't understand how this works. Okay, but every time you run this program for the first time, it did not work. I don't know what magic happened or how it works, or maybe I'm not that good expert in all this stuff. But first time it won't work and second time it worked. So this is like you see here, process is executed and new program user bin dash has been called. Okay, so we have solved this challenge. Now it is saying program is not running. So now you can try running our exploit. It will work. You see, you now run so many times to verify. Like first time it was accident, second time it was luck, third time it was like whatever you want to say. But the exploit will work every time now. You see, the process is started with increase in one PID. Okay, so the fun part here is when you run this like the stack5 and gives our exploit, it didn't give you shell, it don't give you shell, it says illegal instruction. So there is lot of things, lot of videos, lot of research is there on the internet, like ready stack overflow, wherever you want to run. What is this, I mean, why this illegal instruction message is getting and why you don't get a shell. So don't get panic if you are getting this error, because what I understand from this is like the shell is expecting something, some input. Okay, and it is not getting any input from the stdin. That's why the process is getting exited. So now if you see the same, like take dot exploit, uh, okay, it's not working. Now let's try again, it will work. Mm-hmm. Yeah. I know why it's not working. Disassemble main and put the breakpoint here before we exit the program so that we can hold the process of executing shell. Now you go here and continue. You see the shell is called. So after running the shell, it is expecting some input from stdin, and as we cannot give any input from stdin, this issue is occurring. I don't want to destroy my video here, but if you do something like this, it should take this as an input. You see, dash take this as an input, but it is saying no such a file or directory. Cat slash e. What is this? Okay, just take. Let me give this as a ls as an input. Okay, so that error is different. Probably our shell is giving that error. I don't know. Or Let me give an idea as an example. Ambiguous redirect. Okay. Okay, whatever the reason is, we'll figure this out later. Maybe the reverse shell or bind shell can work with this example. So it's a matter of shell code. So shell code is giving you a shell, and that shell is expecting some input. Like this shell, this is my shell code, and this is my shell form shell code. So it should be working. Yeah, it's working. Okay, so I hope you enjoy this video. Thank you. If you have any doubt regarding this exploitation, do let me know in comment. I'll try my best to help you. So do not forget this breakpoint. I spent quite a lot of time solving this. Okay. So our shell is getting executed every time, and it is exiting because it's not getting any input from stdin. Whatever we tried, it didn't work. It's okay. Thank you guys. I hope you enjoy this video.